What are we doing? We're talking about modeling, right? Modeling a system as a single degree of freedom system, okay? And as I introduced last time, we're going to do this in 4 or 3 different ways, depending on the complexity of the structure. And if the structure is simple, if the structure or the system is simple, is not very complex, it's made of 1 or 2 pieces, nicely defined components and whatnot, then the approach, as I said, was that you set up the free body diagram and then directly derive the equation of motion. So what would result will be something like this. So something like this equal to 0. Whatever is a component of the displacement term is the stiffness or the equivalent stiffness of the system. Whatever is a component of the acceleration term is the equivalent mass in the system. I did 1 problem, 1 or 2 problems last time. Let me do maybe 1 or 2 more before we get to the next level of complexity. Let's say you have, for instance, a simple structure that is made of just 2 pieces like this. A rigid bar hanging at this point, pivoting about point A, and supported here by a spring with a given stiffness coefficient. Okay, length of this bar is L, and it has a mass also. Okay, so we want to find the equivalent single degree of freedom system for this and find the natural frequency. So, as I said, for simple systems like this, you just simply set up the free body diagram. So if this is moving back and forth, let's say this is the displacement configuration. Okay, this is the angle of rotation theta. So you just simply set up the free body diagram, right? Knowing that if you put the lumbar force, this becomes, or you can treat that as a static equilibrium problem. So if it is moving that way, the lumbar force, which is I theta double dot in this case, would be this way. I is the moment of inertia of that rigid bar. So you have these 2 forces at this point of connection. You have the mass, mg, and it's moving that way, so the spring is stretched, and it generates a force that is acting in that direction, right? You have all these quantities. This is theta, okay? So this distance would be what? This is L, this would be L over 2 sine theta. And if the angle theta is small, this would be just simply L over 2 theta. How about the displacement of this spring? This would be L sine theta, or if the theta is small, would be just L theta. So that's the free body diagram, right? So once you set up the free body diagram, rest is easy. Summation of moment is a rotational motion, so summation of moment about, say, point A, point of rotation is 0. Okay? So you just simply add up all these forces, moments. You have I theta double dot plus the moment of this about point A, so you have this force mg times this distance, which is L over 2 theta. Then you have this force, Fk, times this distance, which is L cosine theta, but since theta is very small, cosine theta is almost 1. So it would be just L equal to 0. F of K is the stiffness of that spring times the deformation, which is L theta. So let's just simplify this. And I is the moment of inertia of this bar with respect to this point of rotation. So we know this is what? You remember that? Anybody? ML squared over 3. But this, the center is ML squared over 12. So use parallel axis theorem. This is L, half is the distance, so you have to add ML over 2 squared. That would be it. So you have then ML squared over 3 theta double dot plus, I can factor out L here, so I have L times mg over 2 plus k L theta is equal to 0. So as I said, you just compare that with this equation. This is your mass equivalent. This is the K equivalent. Therefore, natural frequency, which is K equivalent over M equivalent, would be simply L and L cancel out, would be mg over 2 plus K L divided by ML over 3. This is the natural frequency of the system. So with this simple approach, easy approach, we can find this equivalent system. In other words, this is the same as this model. Solution for this is the solution for this, where M and K are defined by these relationships. Yes, any questions?
So does that say is L outside the parentheses?
Yes, because this was KL squared, then I had L here, so I factored that out.
Okay.
That's all. Fair enough. Any other question? So let's do another problem. Another example. Let's say you have a rigid bar like this. This is rigid, massless. There's a lumped mass here, a point mass. This rigid bar is pinned here, so there's a pivot point at point A, and a spring is attached to this tip of the bar, the stiffness with a stiffness coefficient K. Okay? This length is A, this is B, and you want to find again, set up equation of motion and find the natural frequency. That means, let's see if I can find a system modeled like this. So I need to find the equivalent stiffness, equivalent mass in order to find the natural frequency. So again, this is a simple structure, so what I will do, I just use free body diagram. So if this is moving, let's say it's rotating like this. So let's say the angle of rotation is theta. Since it's rigid, these two are perpendicular. This angle would be also theta, okay? So the free body diagram would be like this. You have these forces here, AX, AY, mass, oops. Mg, right? And this is moving that way, so it generates a force in this spring. And if this is moving that way, the inertia, rotational inertial force would be this way, the lumbar force. So that is the free body diagram. So that's the free body diagram, okay? Theta and theta, okay? So with that as a free body diagram, just let's apply the equations of equilibrium, which is summation of moments at A is equal to 0. So I will have I theta double dot plus the moment of this force about A, which is in the same direction, f of k times, this is A, so this distance would be A cosine theta. Again, theta is a small, so cosine theta is 1, so it would be just A, okay? What else? Mg, okay, would be the opposite direction, and the moment arm is this, which is, this was B, so it would be B theta is equal to 0, okay? This one doesn't have any mass, so the only moment of inertia comes from this little point mass rotating about A, so that would be mb squared. The force that is produced in the spring would be due to its elongation, and that would be the k times the displacement that this goes through, which would be A theta. Okay, so let's just simplify this, write this, rewrite that, so you have mb squared theta double dot plus, I'll just factor out theta, so you have k a squared, right, minus m g times b theta is equal to 0. Okay, so now that you've written it that way, coefficient of the acceleration term is your m equivalent, and the coefficient of the displacement is your k equivalent. So therefore, natural frequency, which is k over m, would be ka squared minus mgb divided by mb squared. Okay. Of course, we will look at something like this in more details later, because you can see that depending on what the value of these are, if mgb is greater than ka squared, this would be complex, which is okay, but we will see what that means, having a complex natural frequency. Any questions? Okay, so with that said, let's see. This is the first approach. As I emphasize, it's for those cases, we have a simple case made of some simple components, and you can, as long as you can set up the free body diagram easily, you can directly derive the equation of motion, and by comparing that equation with the equation of motion for a mass spring, which is the model that we want to set up, the coefficient for the acceleration term is your mass, coefficient for the displacement term is your stiffness. You can find the natural frequency or you have modeled the system as a single degree of freedom system, so you know what the solution is, or you know how to basically derive the solution for that equation and find the displacement later on, how to basically do all kinds of things with that. But before I go introduce the second approach, or we look at the vibration of more complex system, or how to model that, I should emphasize that we are dealing with basically a one-directional motion, actually throughout the whole course. So either you have a translational motion, a mass going through translational motion, center of mass moves along that direction, or a rotational motion. So you have a mass distributed, moment of inertia, and going through some rotational motion. In either of these two cases, we are dealing basically with a motion that takes place in one direction. So if you have a structure, as you saw here, made of, say, a few pieces, in the example I did, for instance, you had a spring and a rigid bar, you could directly find what would be the total stiffness of the system. The stiffness of the system probably is the more complex part of finding the equivalent single degree of freedom system. So we are going to spend a little bit of time on that today. What does that mean, the stiffness of the system? A system usually is composed of different components. These components can be those structure elements you've already studied. A bar, or a truss element, a beam element, or a shaft element. These are the simple, basically, structure elements you've already seen in your stress analysis course, right? We do know, by definition, what is the stiffness for each of these elements. We describe, as I said last time, we define or describe the stiffness. What is the stiffness? Stiffness for a structural component is what? Is the force causing a unit displacement or unit deformation, right? So for a bar element subjected to the actual load, obviously, that goes through a displacement. If this is L, all the geometric and material properties are given, was what, PL over AE, and therefore the stiffness, if this is 1, K for that is what? AE over L. For a beam element like a cantilever beam, right? This is displaced. Delta is PL cubed over 3EI. So if this would be a stiffness, if this is 1, so K is 3EI over L cubed. If you have a simply supported beam, okay, subjected to a mass sitting here, so it's oscillating like that, and you're concerned about the displacement here under the action of load, right? This maximum displacement here, delta is 48 EI over L cubed. So you can I'm sorry, I wrote the stiffness. The displacement is PL cubed over 48 EI. So the stiffness would be, this is 1, this would be the stiffness, 48 EI over L cubed. For a torsional piece, we saw that. If it is subjected to a torque, this is all the geometric and material properties are given, right? We remember that theta was GJ over L. the stiffness, sorry, the deformation is given, and we said that, theta was tau L over G J. So if this is 1, this is 1, then this is KT. KT is G J over L. So for simple structure element, we know what is the stiffness for, one more time, okay, 4. So what we want to do, or we know, is that if you have now a structure that is made of different components, how you add up these different stiffness components for the structure, for the mechanical vibration purposes. In vibration, we encounter basically 2 cases for the most part. Case 1 is what we say or describe as the stiffness components are what we call in series, or the stiffness components in parallel. What does that mean? There are 2 cases very important that we encounter. Either all the components of the structure are subjected to the same force. If they're subjected to the same force, we say they are in series. And the reason for that is, as we will see, the equivalent stiffness for this case, the way we will derive that would be analogous to the way the resistors in electrical circuits are added up. So since a series combination of those and is analogous to the way the springs in series are, we call this case a series combination, which is meaningless. All that means is that stiffnesses are such that they're subject to the same force. That's a better definition. Parallel means when the components are subjected to the same displacement. In other words, if the components experience the same displacement, the equivalent stiffness is derived differently, okay? So we're going to look at these and then see how these apply to a real case when we have a more complex structure. We want to, for instance, you have a building with all these columns and you want to replace this entire building as a single degree of freedom system. So how do you add up? Of course, adding up is not the right term. How do you find the equivalent single spring element or the stiffness that would do the same job as all these columns combined would do? Or if you have a rotating machinery with all these bearings and supports, can you come up with one single spring to be used for that single degree of freedom system that would do the same job as all these bearings and support would do combined? That's what we want to do. So with that said, let's introduce these 2 simple concepts, which is the first step. So we said that let's consider a case that you have a couple of springs subjected to the same force. So to begin with, I would only consider, let's say, 2. You can have more. Let's say you have just 2 springs that are connected like that, so they're subjected to the same force. The objective is you want to replace these with a single spring whose stiffness we want to find, and we call that equivalent stiffness, okay? In other words, how to find this so that we can replace this system with this system. If these are subject to the same force, that means that each of these springs, because of different stiffnesses, will experience different deformation. This spring will go through a deformation, which is this. This spring will experience a deformation, which is this. And obviously this spring would experience deformation equal to that, right? Now let's look at the, say, free body diagram of each element. So the first spring would be basically subjected as force F, right? So would experience a deformation that follows this relationship, right? U2 minus U1. The second spring, okay, we can write this relationship for that, right? Intentionally, I'm going to rewrite this differently. So in other words, I'm going to write this relationship as this. This is U2 minus U1. This is U3 minus U2. How about for this equivalent system that is going to replace those two? We can write K equivalent, which we don't know what it is, U3 minus U1, or I can write F over K equivalent is U3 minus U1, right? Interestingly enough, you see that if I add these two, in other words, F over K1 plus F over K2, okay, is U2 minus U1 plus U3 minus U2. These two cancel out, so this is U3 minus U1. That means the left-hand side is equal. Since F is the same, so what this leads to is then this relationship. So if you have two springs that are subjected to the same force, the total stiffness of the system or a single spring that can replace those can be derived from this relationship, and this actually can be further generalized. If you have more than two, you can just simply write this as this relationship. This is a generalized form of that, okay? So this is the case, for instance, think of this situation. You have two shafts. A non-prismatic shaft made of two pieces, you don't like that. You want to replace this with a single shaft. Or, in other words, find the equivalent stiffness here for this vibratory motion. So, since these two shafts experience the same force, right, you call them in series. And since they're in series, if you have the basically geometric and material properties of each one, you know that 1 over the equivalent torsional stiffness for that system would be, for this one, you know that is G1, J1 over L1. For this one it was G2, J2 over L2. Okay, so this would be L1 over G1, J1 plus L2 over G2, J2. So you can find a single shaft with that stiffness that would replace these two. Now, what happens if these springs now are, so if I can call this, maybe I can, this was case 1, right? This is case 2. And that is, how about if you have these two springs now that are connected such that they experience the same deformation? Forces are different in these two, but they experience the same deformation. Okay? Now what happens? from the free body diagram, we can see that if this is the total force, this is K, this is basically I would write that as F1, F2, okay? Total force is the sum of the forces generated in each spring. Again, here the objective is we want to replace this with a single spring. Okay? So we know each of the displacement that these experience, okay, which is the same, F1 is K1 times U2 minus U1. F2 would be K2, same displacement, and the equivalent spring would also experience the same displacement, or subject to the same displacement. So if you write this now as, you substitute those into this equation, you can easily see that what results is K equivalent is K1 plus K2. So if two springs are subjected to the same displacement, the total stiffness is sum of those two stiffnesses. Or more than, of course, two springs. You can generalize this and write I is equal to 1 to N Ki. The important thing is that the concept is very simple. The most important part is that you recognize what is the meaning of series or parallel. Or in other words, how do you detect if these stiffnesses are subject to the same force or experience the same deformation? That's the key. For instance, why it is important, because for instance, if you don't recognize that these stiffnesses are in, say, series, you may say, okay, for instance, I have a rotating machinery, and it happens that the support system, these bearings, are series. Okay, in other words, those experience the same force. And you have too much vibration, you say, well, I have to stiffen the system, right? But what happens if you have a weak link in the system? Let's say that system consists of 3 supports. So if you have a weak link in the system, and you want to increase K, you want the total stiffness increase, right? And let's say this is quite a weak stiffness. That's the one that dominates. In fact, here, because imagine if this is very small, right? What does that mean? That this term would be very large, right? So, doesn't matter. If you strengthen these, it is that weak spring that will dominate. So by strengthening the other stiffnesses, it doesn't matter if you have a weak link and you don't recognize that these are all in series, just by strengthening the others, you're not doing much. The point is that you need to recognize whether the springs or the stiffness elements are in series or in parallel, okay? So, and as I said, the geometric configuration doesn't tell you anything. Let's first look at this. You have this beam, okay? You have a mass. You have a bar here, a 2-force member, a truss element, A-E-L. This is a beam, E-I-L, and another spring here. If this is moving, are these in series? They're connected to each other like that, right? Why not?
Because they have the same displacement.
Exactly. You look at it this, you should look at this, you should not let the geometric configuration fool you. Imagine that if this beam goes through a displacement, delta, it is the same displacement that these two also experience. So all these three are actually in parallel. That means the total stiffness would be just whatever you find, 3EI over L cubed, if I call that K1, K2, K3, which would be AE over L, right? Would be K1 plus K2 plus K3. That's how you figure it out. There are two good problems in the homework, so I'm just going to give you a hint, in fact, in doing those, because it's especially problem 110 is a very good problem. So someone brought it up in the other section, so I'm going to give you a good hint to do that. And it's a good example, actually, to do. 110 and 111 both. I think somebody actually asked me the other day about 111. So this is 110. We have a system that is like this. I'm not going to do as good of a fancy job as so you have a disk with a radius r that is going through a rotation theta, and there are these two springs, K5 and K6, connected to that. And this is, in fact, a shaft, a non-prismatic shaft, which looks like this. So each piece of this shaft obviously has different stiffnesses. This is K2, this is K1, and this is K4. So the problem is asking you to find the either the natural frequency or find the equivalent stiffness, which is all you really need, okay? Because you have the mass here, you have the moment of inertia, you can set up the natural frequency as long as you find the equivalent stiffness. See, look at this. If this is turning, okay, all you can say is that these three will be subjected to the same force. Imagine if you apply a torch here, right? These three will experience the same force.
The one on the top too, right?
Well, let's go step by step. Right? You can say that these three are subject to the same force, right? So the equivalent stiffness, if I can call that K prime, for these three would be what? 1 over K1 plus 1 over K2 plus 1 over K3. So that you can find K prime, and therefore you can replace this now with just one shaft. So this would be now K prime. Now, what can you tell about these two? Let's do a two-dimensional thing here. If I'm turning this, can I say that the forces in these two are equal? You can. All you have, because it's the first one indeterminate structure, right? But you can say both experience the same deformation, right? Because whatever this is, you're turning this, right? You're constrained. So whatever amount this turns, this would turn the same thing. So now these two are in parallel, or if you use that terminology. So if I call replacement for these two, okay, K double prime would be K4 plus K prime.
Wait, I thought you said.
They go through the same deformation.
Well, I thought you said they had the same. Didn't you just say they had the same force?
These have the same force,
Okay, but K prime and K4.
but the force here and here, we don't know if it is the same.
Okay.
But we definitely know this has a force, this has a force. But this force and that force is not the same, okay? Yes?
One more time, where did you account for K4 and K6, K5 and K6?
Oh, I haven't got there
Oh, we
yet.
haven't got
No,
there.
no, not there yet. Now, in order to get there, right, if this is turning, right, K5 and K6 will be experiencing, again, the same deformation. Because they're going through a deformation which is what? R theta, right? R theta is what K5 and K6 will be experiencing. So we know that they are in what? You're in parallel. Geometric configuration is neither parallel nor series, but based on the conceptual meaning of those cases, these two experience the same deformation, so they're in parallel. So you can write, I can write that as K double prime is K5 plus K6, right? But now, you have this guy, how do you add these up, right? The force that with these two experience, right? If this is subjected to, let's say, a moment, would be, in other words, moment about this point would be F times R, right? So in other words, each of those springs, or the equivalent spring, what did I call it? K prime, would be subjected to a deformation R theta, okay? So the force that it generates would be K R theta, okay? But the moment that then this shaft is basically subjected to, if you consider that, would be F times R, okay? So that moment would be K prime R squared theta, okay? Yes?
Is this, A double prime K5 plus K6 or K double prime K4 plus K5?
I called this one K4 plus, oh, I already used K double prime, so I would use triple prime. Okay.
So
I
then
ran out of-
everything on the right,
Everything on the right is triple prime.
okay.
Right, right. So left, I'm gonna leave it to you. Just one more step to complete that problem. Okay? There's another good problem, problem 110. I think I had the problem mistaken here. Okay. Okay. Okay, problem 10, no, 111, I'm sorry. Problem 111 is something like this. You have a mass sitting in the center of this beam. First, I guess the problem is asking you to find the equivalent stiffness of this. Well, this is going to experience a displacement. In other words, the mass experiences this as a result of this weight. The structure would experience a displacement here, which is the maximum displacement, right? Delta PL cubed over 3EI. So the stiffness is what? 3 EI over L cubed. So that is the stiffness of this beam, okay? The second part, so we can substitute and find that. Then, the second part, it is asking you how much is the displacement, this displacement due to this mass, right? If this is the stiffness, right, what that means is you just have a mass and you have this stiffness, you want to know how much is this displacement, delta. That's what problem is asking you. So, what is it? Force is K times displacement, right? You have K from here. What is your force? Is mg. So delta would be mg divided by that K. Then in the second part of the problem is asking you if we put a spring in the middle of that beam, okay? If you put a spring here, okay, find the spring constant that we need in order to reduce the displacement by 25%, 50%, and 75%. In other words, whatever this is, let's say this comes out to be 3 inches, I don't know. How do you reduce that by 25%? By finding the right stiffness. First of all, when you put a spring here, right? So what would be the total stiffness now? They are in parallel. Because the beam and the spring are going through the same displacement. So the total K, would be K plus whatever you found here, 3I over L cubed. So delta, now, you have this mass, you have this equivalent stiffness, right? You don't have this one, right? If it is reduced by 25%, that is, you know that, say, 3 inch minus 0.25% times 3 inch, whatever that is going to be what? Is going to be a new displacement, which is mg over this K plus the K equivalent, where K is 48 EI over L cubed. So you have M, you have G, so you find, I'm sorry, this one is K equivalent. Okay? You have that, you find this. Okay? For 3 cases.